When we talked about multiplying whole numbers, we said that the numbers being multiplied are called factors, and the answer is called the product. But suppose we want to write all of the factors of a particular number. Like suppose we want to find all the factors of 12. Now that would be all of the numbers that could be used as multipliers, you see, to give 12. So we might reason this way. We might think, well, we can think of 12 as 1 times 12. That is, 1 times 12 is 12, so here are a couple of factors of 12. 2 times 6 is 12, so here are 2 more factors of 12. 3 times 4 is 12, so here are a couple of other factors of 12. Now these are all ways that we know right now to multiply to get 12, so I might put these in a list. These are then all the factors of 12, 1, 2, 3, 4, 6, and 12, if I'm listing them in order, and these then are the factors of 12. We might notice that these numbers also are numbers that go into 12 a whole number of times. You see, if they are multiplied to get 12, then each of them must go into 12 a whole number of times. And that's an interesting idea because it gives us another way to find the factors, because we can find factors by just finding divisors. Factors and divisors are fairly interchangeable then in this process. Okay, if we want to find then the factors of 18, rather than writing numbers that multiply to give 18, we could reason this way. We could say, well, let's see. 1 goes into 18 times, you see, and therefore 1 and 18 are factors of 18. What about 2? Yep, 2 goes into 18 9 times. So 2 and 9 are also factors of 18. How about 3? Yep, 3 goes into 18 a whole number of times. Goes 6 times. 3 times 6 is 18. So 3 and 6 are both factors of 18. Is there another one? Let's see. The one after this would be, well, how about 4? No, 4 doesn't go into 18 a whole number of times. 5 doesn't go into 18 a whole number of times. How about 6? Well, 6 goes into 18 3 times, but gee, I already have 3 and 6 written right here, so I don't need this. All right, so I have all of my factors of 18 listed here. And if I want to write them in order, I can write them as 1, 2, 3, 6, 9, and 18. So 1, 2, 3, 6, 9, and 18 are the factors of 18. Now, when the numbers get a little bit bigger, we need some techniques for 2 things. One is to try to decide whether numbers go into a particular number. Like we can see that 2 goes into 18, and we can see that 3 and 6 go into 18. 18 is a small number, and we've worked with it a lot before. But what if we have a 3-digit number or a 4-digit number? Do we know whether 3 goes into that number, or 2, or 5, or something like that? Well, it turns out that we have a divisibility test. We have a test that we can perform to tell us whether or not we have divisibility. Now, the divisibility test for 2 is fairly easy. If the number is an even number, then it is divisible by 2. So all we have to do to look to see if it's an even number is look at the last digit. If the last digit is an even number, 0, 2, 4, 6, 8, then we know that 2 will go into that number. All right, that's pretty easy. There is also a divisibility test for 3. And the divisibility test for 3 is this, that if you take the digits and you add them, you see, and you get what's called a digit sum, and if 3 divides the digit sum, then 3 will divide the number itself. It even works here on 18. The digit sum would be 1 plus 8, that's 9. Does 3 go into 9? Yep. So 3 goes into 18. You see, if 3 divides the digit sum, then 3 divides the number. The divisibility test for 5 is pretty easy as well. 5 will divide evenly any number which ends in a 0 or a 5. That is, if the last digit is a 0 or a 5, then 5 will go into that number an even number of times. Or, excuse me, a whole number of times. All right, let's go through and find the factors of 165. And by the way, I said that there were 2 things that were important in this process. One is this divisibility test idea, and the other one I'm going to bring up here with this problem. And it's this: how far do you have to go in your testing? You see, how far do you have to test? When the numbers get big, that's a very important issue. All right, here, if we're thinking about the factors of 165, well, we know that 1 goes into any of the numbers we're going to talk about. So this is a trivial situation. 1 and 165 are both factors of 165. All right, what about the next number? Well, 2. Does 2 divide that number? Well, no, because it's not an even number. Does 3 divide that number? Let's use the divisibility test. 1 and 6 is 7. 7 and 5 is 12. 12. Does 3 go into 12 a whole number of times? Yes, it does. So 3 will divide that number, and so I know that when I divide 3 into 165, it'll go evenly, and therefore, when I say go evenly, I don't mean it's an even number. I mean it goes a whole number of times. All right, so 3 into 165 turns out to be 55. So 3 and 55 are factors of 165. Now, what about 4? Well, 4 certainly doesn't go into that number because it's not even. What about 5? Well, 5 will divide it evenly because the last digit is a 5. If it's a 0 or a 5, 5 will go into it. So 5 will go into it, and it turns out that it goes 33 times. What about, well, we don't have a divisibility test for 7. We would have to actually try 7. 7 doesn't divide it evenly. How about 9? Now notice that I'm skipping over the even numbers because I know that since it's not an even number itself, even numbers won't go into it. But 9 doesn't divide it. 11, well, 11 turns out to divide it. 11 into 165 goes 15 times. All right, now how far do we have to go with this process? That's the next question. And to answer the question, let's come back over here with 18, and I want to talk about it in terms of this problem. Notice that when we got to this point where we had 3 into 18 is 6, and then we moved ourselves up to 6. 6 and 18 goes 3, and we sort of get the same two factors just kind of swapped that we have up here. All right, now, there must be a spot somewhere in between the 3 and the 6 here where we could have stopped. And it turns out that if you'll kind of look at the pairing here, 1 with 18, 2 with 9, notice that the value of the factors is farthest apart here and getting closer and closer together. And it turns out that you needn't go any farther than a position where the number that is the divisor and the number that is the quotient here would be identical. That is, if the number here times itself is 18 or bigger, is bigger than 18, then you don't need to go any farther. Okay, the number that you're dividing by squared is bigger than the number you're talking about, then you have gone far enough. When we were trying 4, for example, or when we were trying, if we were to try 5 into 18, then 5 times 5 is 25, we've gone far enough. You see, we don't need to go farther than that. Okay, that's a handy idea when we get to a number like 165. Now, let's see, what number squared is bigger than 165? We haven't dealt with these very much. Now, let's see, we know that 12, well, we may know. We know that 10 times 10 is 100. We know that, we may know that 11 times 11 is 121. 12 times 12 is 144. We're getting pretty close. 13 times 13, let's grab the calculator or let's do it on a little sheet of paper or something. We find out that it's 169. Now, 13 times 13, 169, that means we don't even need to go farther than 13 in our testing for the factors of 165. And we have therefore identified all of the factors of 165. 1, 3, 5, 11, 15, 33, 55, and 165 are the factors of 165. All right, that's the idea. Some numbers have very few factors. The factors of 7, since 7 can be, we can think of 7 as 1 times 7, or if we are looking for items to be multiplied, whole numbers that multiply to give 7, it's just 1 times 7. And that's the only way we can cook this rascal up to get 7. There's no other combination that will give 7. So the factors of 7 are just 1 and 7. Now, whenever we have numbers where the factors of the number are just 1 and itself, that number is called a prime number. So 7 is a prime number. Now, some other examples of prime numbers are these. Now, the first prime number is 2. One is not prime, and it falls into a category unto itself just about. But prime numbers begin at 2, and then 3, and 5, 7, 11, 13, 17. All of these numbers have the characteristic that if you were listing all of their factors, all you could list would be 1 and itself. You see, 1 and itself are factors of these numbers. Now, 2 is not only the first prime number, but it's the only even prime number. After all, for every even number after 2, not only 1 and itself would go into that even number, but 2 would go into it as well. So it would fail to be a prime number. So 2 is the only even prime number. Now, numbers that fall kind of between these are called composite numbers. And numbers that are larger than 1 fall into one of those two categories. They're either prime or composite, you see, and these are the prime numbers. And by the way, there are an infinite number of prime numbers. Well, one technique that we want to talk about concerning prime numbers is this, that it turns out that numbers that are not prime, composite numbers, can be written as the product of prime numbers. Wow. They can be split up so that we write them as the product of prime numbers, that is, prime factors for every factor. For example, a number like 6 can be written as 2 times 3. Notice 2 is a prime number and 3 is a prime number. So this is a product of prime numbers for 6. Now, this is called a prime factorization. We are factoring 6 as a product of prime numbers. Now, let's talk about 30. And there are a lot of nice little techniques for going through a prime factorization. I want to show you a couple of them. There's an interesting one in your textbook, and I invite you to have a look at that. They all pretty much do the same thing for us. But let me show it to you. You can kind of take your choice as to which one you want to use. This is an interesting one. Suppose we take 30, and now remember, factors and divisors are interchangeable, so we can attack this as a division problem if we want to. We can think, well, let's just take the smallest prime number, which is 2, and see if it goes into 30. It does, because 30 is even. But we can write this then as 2 goes into 30 15 times. And then you look at that number and you say, well, does 2 go into that? No, it doesn't. Does the next prime number go into that? Next prime number is 3. Yes, 3 goes into 15. And let's just divide it like this. And we can kind of stack the division this way. You see, so 3 goes into 15 5 times. And when you arrive at a point where the topmost item is a prime number, then your product of prime numbers is right here. You see, we can write 30 as 2 times 3 times 5. Let me write that over here. 2 times 3 times 5 is the prime factorization for 30. Let's look at another technique for dealing with 30. This is one that I particularly like. I like the idea that we can take 30 and we can write it as some product over here. Now, generally, to have some kind of pattern for this thought process, I like to start with the smallest prime number. I like to start with 2 and then say, does 2 go into this number? If it does, then I can write the number as 2 times some other factor. And I would do that like this. I'd say, well, yeah, 2 goes into this number 30 15 times. So 2 into 30 is 15, so I can write 30 as 2 times 15. And now I'll look at 15. You see, it's very similar to this, but it's in a more, mathematical way here with this kind of equal sign. This is equal to the product of those, and now I'm going to come down and bring down the 2 and then subdivide the 15, you see, and think to myself, well, does 2 go into 15? No. Does the next prime number 3 go into 15? Yes. How many times? It goes 5 times. So 15 can be kind of split up into 3 times 5. You see, like that. So we get the 2 times 3 times 5, boom, just like as we have over there. A third technique, another technique, and I've seen this used very effectively as well, is this, that you take the number and you just start to split it up. And you kind of make some branches here of factors. And you might say, well, 30 is 5 times 6. Okay, and then, but that one's prime. Now, what about this one? Oh, that's not prime, but I can split it up. I can split it up into 2 times 3. You see, so it's the idea, and for emphasis I'll put the dots in here, but it's the notion that we have a branching situation, and once you've arrived at a condition where the ends of the branches are all prime numbers, then you have your prime factorization. Our prime factorization is 5 times 2 times 3, which is what we have over here. So any of these methods work really well. How about 24? Now for 24, once again, we can use any of the methods. I'm going to use my favorite, and my favorite is one where we do this. 24 can be written as, I would ask myself, does 2 go into 24? Yes, it does, because it's even, and so I can write 24 as 2 times 12. And then I would say, does 2 go into 12? Yes, it does. It goes 6 times. So I can write 12 as 2 times 6. Now, notice in this process, I bring down the prime factor that I already have, and I'm just splitting up 12 into 2 times 6. And now, my next thought is to bring down these 2 prime factors and then divide 6, you see, into 2 times 3. And now I have my prime factorization. And I can kind of consolidate things using exponents, can't I? Because after all, I have 3 factors of 2, and then I have 1 factor of 3. So I can write this as 2 cubed times 3. And that's what I would want to write over here, 2 cubed times 3. All right, so that's the idea. Here's a rather big number, 101. Wow. Okay, let's try our prime factorization. I would be thinking this way. For 101, does 2 divide this number? No, it's not an even number. Does 3 divide the number? Let's check out the digit sum. 1 and 0 and 1, that's 2. So the digit sum is 2, and 3 does not divide 2 evenly, and therefore 3 does not divide 101. All right, what's the next prime number? Now, remember that we're not looking for all the factors. We're looking for prime. We're only checking out primes here because we're doing a prime factorization. So we're thinking about prime numbers. And I've checked for 2. I've checked for 3. The next prime number is 5. But 101 has as its last digit a 1, so 5 doesn't go into it. The next prime number is 7. I might try dividing 7 into it. 7 into 101. 7 into 10 goes 1. 1 times 7 is 7. Subtract, I get 3. Bring down the 1. 7 into 31 goes, 4. 4 times 7, 28. And I subtract and get 3. So it doesn't go a whole number of times. I get a remainder, you see, and so 7 doesn't go into that. I can't split it up using 7. Next prime number is 11. Does 11 go into it? Well, once again, I could try dividing by 11. But you know what? I might start to think about how far I have to go with this process. Now, how far I have to go with the process is the same as it was before. I need to test up to that point where I'm testing a number which when squared gives a value greater than 101. Now, 10 squared, we didn't try 10 because 10 isn't prime, but 10 squared is 100, and this is just 101. So as soon as we get to 11, we've gone too far. You see, we've gone to a point where the other factor would be smaller than the one that we're using to test, and so if it were valid, then we would have already found it. You see, that's the idea. So 101 has no prime factorization like we've had over here. 101 then is a prime number itself. You see, we can't do a prime factorization here. The only factorization we can do is 1 times itself, 1 times 101. So we would say here that 101 is a prime number. Or simply, 101 is prime.